Assalamu alaikum. This is third lecture in the series of lectures on chapter 10. In this lecture, I will discuss data comparison instructions and just see the comparison of green and red apple. Enjoy. Data comparison instructions. Normally you know them, but we will repeat just for recalling. Equal, not equal, less than, greater than, less than or equal, greater than or equal. In RS Logix 500 software, when you click compare, you will get these tabs. The first tab is limit. If the comparative data is within the range of the limit, the rung will be true. Then the other one is masked equal. Partial data is masked and the rest of the data will be compared. And if the comparison is equal, the rung is be considered true. Equal instruction. In the equal instruction, if in two registers data are equal, then the rung is true. The other one is not equal. Here if the data in two registers is not equal, the rung will be true. Less. If data in the first register is less than the destination register, the rung will be true. Greater. If data in the source register is greater than data in the destination register, the rung is true. Less than or equal, it is similar to the less. The only difference that even if the data is equal in two registers, even then the system will be giving us true rung. And greater than equal is similar to the greater, only difference is if the data is equal in the two registers, even then the rung is true, while in less and greater the rung will be true if and only if the datas are less or greater. So this is the format of the equal instruction. We have source A and source B. Now in source A, suppose we have moved the data from T4 accumulator, and in source B we have moved the data from N740. If data in A and B are equal, this means the rung is true, so the pilot light will be on. But if data in source and A and data in source B, if they are not equal, the rung is not true and the pilot light will be off. So here I will explain the move instruction and equal instruction together. So the source is I colon 5. This means it is the complete register. Now there is initial value is 0. So if you look here, it is 0, 0, 0, 0. And this is I5 register. And when we say I5 register, this means from 00 to 15. So this complete word is I5. Similarly, O6 is the destination, and it is by logic we converted the byte into the BCD. Similarly, this is input from the hexadecimal to BCD, and this is also a BCD. Now, whenever the move instruction is working, so whatever the data we will write here, you can see the data over here. And this is because of this move instruction, because the move instruction moves the data from the input register I5 to the output register O6. Now here is the equal instruction and S1. So S1 is I1 and it is 1 bit address, and equal is the complete equal instruction. So whenever S1 is true and equal is true, this is AND instruction because they are in series, then the pilot light will be on. So to make the pilot light on, the data in A colon 5 register should be equal to the data already inserted in the source B, which is 4616. This is the BCD data, and the same data in hexadecimal is 1208 in hexadecimal. So let us try to run the simulation. So in the simulation, so here whenever we are going to change a number, so you see the same number change over here, and fundamentally the number is changing in I5, and the move instruction is going to move it here, and I5 is here, the same number is appearing. Whenever the data here and here is equal, this will become on because this switch is closed. But whenever the data here and here is not equal, so the light will be off. But the second thing, S1 we need should be closed to make the full rung true. So this is the not equal instruction. If in the data in source A and source B is not equal, this means the rung is true and the pilot light will be on. So this is just opposite to the equal instruction. So here whenever the data is not equal here and here, so the pilot light will be on. So it is clear. So whenever here we put the data 25, so not equal, this means with 20 it is on. If we put over here 25, so this light will become off. So similarly, this is greater than instruction. So now if data in source A is greater than source B, the pilot line will be on. Otherwise, the pilot light will be off. So the rung will be true whenever A is greater than B. Here in the A, somehow we put the values which are available in the accumulator of the timer, and this instruction you can use for controlling a certain time and equipment using the timer. So here we explain the greater than instruction. So here it is written T4 colon 10 point ACCC. T4 colon 10 is the address of this timer, and accumulator is the accumulator over here. Initial value here and here are 0. This timer will be enabled whenever I colon 1 oblique 0 is closed. This is the switch. So when we close this timer will be enabled and it will start to run. So the enable bit over here will become high. The timer is running, so TT will be high. TT will remain high until and unless the timer is running. Whenever the value preset value and the accumulator value become equal, the done bit will become high, but the TT will become 0. And then we have the preset value. This, we can enter it over here. Here it will display the ACC, the accumulator value. Let's see how the simulator is working. So here, as soon as we press, it is enabled. TT is 1. So whenever this done bit will complete, at that time TT will become 0. Now suppose it is running, it will remain 0. But if it reaches to 300, this will become 1 and this one will become 0. So here the instruction is LES, to what we say less than. If source A value is less than source B value, the rung will be true and the pilot light PL1 will become on. So in this example, we explain the less than instruction using the counter accumulator, and you have studied the counter previously. Whenever the value in source A, which is C5 colon 10 dot ACC, the value originally this one C5 colon 10 dot ACC. So whatever the value you will see here, this is the same value over here. So whenever the data is less than 5, the pilot light will be on, but whenever the data become more than 5 phase source B, the pilot light will become off, and these registers you have studied before. So let's see the simulation. This become off. So this is the greater than or equal instruction. So the only difference with the greater than instruction and greater than and equal is that whenever A and value of A is greater than or equal to B, the rung will be true and the pilot light will be on. Otherwise, the pilot light will be off. But whenever it is only greater than, then the equal, whenever they are equal, even then the rung will be false. So here we see that whenever this and this data is equal, the light is on, and whenever this become greater than this, even then the light will be on. But the time whenever this value become less than the source value, at that time it will be off. Like now 20 is less than 23, so the pilot light is off. So less than or equal instruction is similar to greater than or equal. Now just if the data in A is less than or equal to the data in B, the pilot light will be on, otherwise it will be off. So this program uh, is somehow like this. We have less than or equal, and the accumulator value is the accumulator of this counter. If the value in source is less than or equal to 5, the pilot light will be on, otherwise it will be off. I10 as many time we close and open them, so it will make the system count, and to reset it we can use the I11. So let's see the simulation and just notice over here, like if it is from 0 to 5, this will be on, but whenever this becomes 6, at that time the pilot light will be off. So Now we will discuss the limit instruction. In the limit instruction, if the test data is higher than the lower limit and less than the upper limit, the rung will be true, otherwise it will be false. So here the lower limit is 25 and the higher limit is 50. So 48 is between the lower and the higher limit. This means it exists in this. So the rung will be true whenever any number between 25 to 50 is there. If it is less than 25 or greater than 50, the rung will be false. So here is the simulation. If here you are seeing 48, so this means 48 is between 25 and 50. This is why it is on. Now if you put 51, this will become off, and whenever we make it 24, this is less than this, again it is off. Now 37 is between 25 and 50, so this is on. So to create the situation in which if the the, the lower limit, if it is greater than the higher limit, then originally the false will be between 50 and 100. But if the test value is greater than 100 or less than 50, the rung will be true. So this is just the complement of the previous limit. Just note over here, the lower limit is higher than the higher limit. So any data in between them will be false and the opposite to that will be true. So here if we see, this is the lower limit and higher limit, and lower limit is more than the higher limit. So any data whenever it is higher than lower than 50 and greater than 100, then this will be on, otherwise it will be off. So anything between 50 and 100 will be false and all other values will be true. So 15, so this means it is on. For more than 100 it is on, for less than 50 it is on, but between 50 and 100 the system will be off. So the mask equal instruction fundamentally compares portion of the data. The masked portion will not be compared, and the other data, its source and at the compare register will be compared with one another, and whenever that portion is equal, this means the rung will be true, otherwise it will be false. So here is an example. The mask over here is all ones, but the last byte is 0, 0, 0 and 0. This means at the source, whatever the data is here and here, irrespective of one another, it will be not compared. But this portion will be compared. So if this data is equal to this, the rung will be true. But if this data is not equal to this, the rung will not be true. So here we put 1 byte, but it is not necessary that it should be 1 byte. It can be any number of bits between 0 to 15 within the register. So we can mask portion of the data, and the portion of the data will be transparent. So the transparent data will be compared and the masked data will not be compared. So here is the simulation for the previous example. So here we see that the mask register is 000, so this means this data will not be compared and the rest of the data will be compared. So whenever this register up to this become equal, this will be on, otherwise it will be off. So with this, the section 10.3 topics are completed. So in next lecture will be section 10.4. Thank you very much.